Hello everyone, welcome to GATE Pass. In this video I am going to take the remaining two problems which appeared in GATE 2016 and that were related to thermodynamics. So the first problem which I am taking is question number 32. This question, let's go through it. So there is an ideal gas in a closed system and it is compressed adiabatically and irreversibly. So they have given you following data set, that is the work done for the irreversible process, that is equal to 1.5 times the work done in a reversible process. So if the same compression was carried out through a reversible process, then W reversible means the work which will be required at that point, okay, in that process. So W irreversible is equal to 1.5 times the W reversible. Now CV, they have asked you to assume constant, its value is given, the numerical value of R is given. Further they have said that the ratio of Cp by Cv, that is equal to 1.277. Okay, so the question asks you to calculate what will be the final temperature for the irreversible process. Now the thing is, we will have to first calculate what is W irreversible. Okay, since there is no formula, there is no equation with which I can calculate my W irreversible. So what I will do is, I will assume that this compression is being carried out reversibly. I will find out the work done for that reversible process and then use this equation to calculate W irreversible. Then from this W irreversible and using first law, I will calculate the final temperature. So let's go ahead and dive in this problem. So on a PV diagram, I have plotted a reversible process. So now the compression is taking place between from P1 to P2, that is from 3 bar to 6 bar. Temperature, initial temperature given is 300 Kelvin. Okay, they have not given any information about V1, V2 and also T2 is not known, okay, even for this reversible process. So keep in mind that this T2 which is there for the reversible process, it will be different for the T2 which will be reached for irreversible process. As we go through this problem, we will see why this happens. Okay, so let's first calculate what is your W reversible for this process. Now since this is a adiabatic process, and you all know that for adiabatic process, your work done, that is equal to R times T2 minus T1 upon gamma minus 1. So this is the equation which is very easy to remember. Usually I remember this equation for the work done in a adiabatic process, okay, and then I derive it then and there what will be the equation in terms of your pressures. But if you want to remember that equation which is given in terms of pressure, then I am going to write that equation as well for you. So that equation takes the form of R times T1 upon gamma minus 1 P2 upon P1 raised to gamma minus 1 upon gamma minus 1 and whole thing in bracket. Okay, so this is the equation. If you can remember this equation, it is fine, okay, but I will quickly derive this from our starting equation. Okay, so let's say I am going to take out T1, so RT1 that is equal to upon gamma minus 1, that is equal to T2 by T1 minus 1. Okay, now since this is an ideal gas, I can apply ideal gas equation and write P1 V1 upon T1, that is equal to P2 V2 upon T2. Okay, so I want this ratio, so I am going to write T2 by T1, that is equal to P2 V2 upon P1 V1. Okay, now I will just eliminate this ratio of V2 by V1 in terms of P1 by P2, okay. Using this equation, what we have for adiabatic process, P1 V1 raised to gamma is equal to P2 V2 raised to gamma, or I can write P1 by P2 that is equal to V2 by V1 raised to gamma, okay. Now if I take gamma this side, what I will get is P1 by P2 1 upon gamma, that is equal to V2 by V1. So I am going to put it over here and what I get is that P2 by P1. So this is P1 by P2. I will take inverse. So I will write P2 by P1 raised to minus 1 upon gamma. Then add these because the bases are same. So 1 minus 1 upon gamma, so that will be gamma minus 1 upon gamma. Okay, so you have this ratio T2 by T1, that is equal to this much, and so I can write my W reversible, that is equal to R T1 upon gamma minus 1, P2 upon P1, gamma minus 1 upon gamma minus 1. Okay, so if you don't remember this equation in the exam, it will take only 1 minute to reach this equation. This equation is simpler to remember. Okay, so that's what I do. So I have now my W reversible equation. So now I am going to calculate what is my W reversible. Since I have written this equation over here, I am going to erase everything. Fine. Now just plug in everything. What is R? 8.314. What is T1? T1 is 300 Kelvin. Gamma minus 1, that is 1.277 minus 1, so I am dividing by 0.277. P2 by P1. P2 is 6 bar, P1 is 3 bar, so P2 by P1 is 2, and that is raised to gamma minus 1, so 0.277 upon 1.277 minus 1. So in one step, you should be able to calculate what is the reversible work which is done, and its value comes out to be 1460.9 joules per mole. Okay. Now your W irreversible will be 1.5 times of your W reversible. So do that and you get the value of 2191.36 joules per mole. Okay. So you have calculated what will be the work which is required in order to bring about the compression of this ideal gas irreversibly. Now we will write our first law, which says that the change in the internal energy, that is equal to Q plus W. Since it is an adiabatic process, so Q goes to 0, there is no heat which is going into the system. So when I am writing my first law, I am following the sign convention that heat going into the system is positive and work done on the system is positive. Okay, that's why I have written Q plus W. Now for an adiabatic process, Q is equal to 0. So what I am left with is basically that your change in internal energy, that is equal to work done. Okay, now this work done can be reversible or irreversible. Okay, so now I have this equation. Further, for an ideal gas, you know that change in internal energy, it is always given as CV into delta T. So I can write delta U as CV into T2 minus T1, that is equal to your work done. Okay, since I am calculating for the irreversible process, I will say T2 irreversible, that is equal to, now over here also it is irreversible work. So plug everything over here, and then what you find is that your T2 irreversible, that is equal to 373 Kelvin. Okay. Now let's understand this problem. So this was the final answer which was asked for. Let's spend 1 more minute to understand this process briefly. Okay. So let's say what will be the temperature if this process was carried out in a reversible way. Then what I will do is I will use the same equation CV T2 minus T1, that is equal to W reversible, and if I put everything over here, that is T1 is equal to 300, the CV value which is given, W reversible which comes out as 1460.9, then the final temperature which I get for the reversible process, that is equal to about 300 and let me check. So it is about 348.7 Kelvin. Okay. So what you see over here is that the gas has risen to a higher temperature when it is compressed irreversibly as compared to when it is compressed reversibly. So let's understand what is happening in this process. That you are doing more amount of work in the irreversible process as compared to a reversible process. Okay. So what is happening is that where is this extra work which is going? Okay, this extra work is being used to overcome the friction. If suppose you are compressing it in a cylinder piston arrangement, so there must be some frictional losses. Okay, further there can be viscous dissipation and all those things, right? So there are certain irreversibilities in the system. Okay, and because of that you require more amount of work than which has been required in a reversible process. Okay, so that extra amount of work which is used, okay, where does it appear? It appears over here. So what happens is that the heat which is generated because of these frictional losses and all, it cannot escape the system because it is being carried out in a adiabatic process. Okay, so your Q is 0. So what is happening? That extra energy which you are supplying, it goes in and is reflected as an increase in the internal energy of the system. Okay, and since you know that for an ideal gas, the internal energy is a function of temperature only. Okay, so that's why what you see is that for a reversible process, your increase in internal energy is higher. So that's why you have a temperature which is higher for an irreversible, final temperature which is higher for an irreversible process as compared to the final temperature which would have been reached if the process was reversible. Okay. So the second problem which I am going to take today is question number 33. Okay, so I will briefly describe the problem. So what you have been given is that a gas, it obeys Clausius equation of state which is given like this, where V is the molar volume and B is a parameter which is a function of temperature only. It is given as Bt, that is the function of temperature, that is equal to B0 plus B1T, where B0 and B1 are constants and their values are given. Further, they have given that this particular partial derivative of H with respect to P at constant temperature, that is equal to this function. Okay, so this equation, it is already given. Now they have asked you to calculate what will be the I think it should be HI. What will be the difference in the final and initial molar enthalpies for this gas if it is compressed from 5 megapascal to 15 megapascal. Okay, so the question is very straightforward. It does not require any knowledge of thermodynamics. It's just mathematical manipulation. In order to find the change in enthalpy, first of all we will have to evaluate the RHS in this equation. So let's do that. For that we will use this equation, that is the Clausius equations of state. So I'm going to write it in terms of V. Okay, so it gives me V minus Bt, that is equal to RT by P, or I can write V is equal to RT by P plus Bt, that is equal to B0 plus B1T. Okay, now we want this derivative. So let's take a derivative of B with respect to T at constant pressure. Okay, so I'm going to take del V by del T at constant P, that is equal to R by P, this is a constant, plus B1. Okay, now let's put the value of V and del V by del T in this equation. Okay, so what I get is del H by del P at constant T, that is equal to V. So I'm going to put it from here. V is equal to RT by P plus B0 plus B1T. Okay, minus T times this derivative. So this is the value of derivative. I am going to just multiply it with T. Okay, so this is what you get. Now you will see that some terms are cancelling and you are left with only B0. Okay, now I can write this as dH, that is equal to B0 dP, or if I integrate it, I am using capital P. If I integrate it, okay, from HI to HF, so it will be Pi to PF. So what will happen is HF minus HI, that is equal to B0 times PF minus Pi. What is B0? B0 is 4 into 10 raised to minus 5. What is PF minus Pi? That is 15 minus 5. Okay, this is your final pressure, this is your initial pressure. 15 minus 5, that is 10 megapascal. So it will be 10 into 10 raised to 6. Okay, do this, it will be 400 joules per mole. So just keep in mind everything is in SI unit. Okay, nothing else in this problem. So this was a very straightforward problem. It didn't require any knowledge of your thermodynamics. It was just a mathematical manipulation. Okay, so there is no point in going wrong anywhere. So these were the remaining two problems which appeared in GATE 2016, and from next video onwards I will be starting the problems that appeared in GATE 2015. So I hope you understood what I am teaching, and thanks for watching, and please don't forget to like this video and subscribe to my channel. Thank you very much.